Okay, mathematical modeling will be the subject of today's lesson. Our problem is bungee jumping problem. You can see on the right-hand side, you might be familiar with this sport. Let's say, I'm not sure it's sport or not, but it's just an extreme sport if we count it as a sport. Now, I'd like to estimate the terminal velocity. Okay, terminal velocity. As you might expect, when this guy jumped from a balloon, for example, or a bridge, let's say, then the speed somehow increases with the force, the gravity, and he would like to estimate the speed, the velocity of this guy at a time instant, let's say t, after he or she jumps. Mechanics says that this, or let's say more correctly, fluid mechanics of physics propose a mathematical model for this problem, and it says that the time derivative of the speed, velocity, is going to be g minus cd over m times v squared. So that's a differential equation. And there might be an analytical solution to this problem, to this differential equation. There may also be a computer-based solution to this problem, what we call numerical solution. Here, v is the velocity, g is the simply the acceleration due to gravity, which is a constant of 981 meter per squared, and the CD, which could be unfamiliar with an electrical engineer, lumped drag coefficient, simply drag coefficient. So once we know this drag coefficient, which is quite related to the body, the shape, geometry, many other parameters, and what we call lumped. So that is an approximation, actually. In most of the platforms, air platforms, drag coefficient is not easy to calculate. Anyway, for human body, it's approximated to a number. And m is the mass. Okay, mass. Which is in kilogram. So, within the next 2 weeks, we'll be somehow dealing with this jumping problem, bungee jumper problem, and would like to use this physical system. This is a physical system. Some features of physics, we'd like to formulate a mathematical equation. So this was actually given here, but we will be looking at how we solve this mathematical equation, or how we model this physical model such that we can use computers to estimate terminal velocity. Okay. Then let's see what a mathematical model is. A mathematical model is a formulation or equation that expresses the essential features of a physical system or a process in mathematical terms. Here you can see a simple functional relationship. We have a dependent variable here, independent variable here, parameters, and forcing functions. So this should somehow expresses the essential features of a physical system. In our bungee jumping problem, for example, this independent variable will be time. The parameters could be the properties of the physical system. For example, here is drag coefficient. Forcing function will be the force due to gravity. So we can think about G here, right? And our dependent variable is the velocity, which is time varying function, actually. So somehow this mathematical model expresses the bungee jumping system. Okay. Okay, let's see the solution to this system. As we said earlier, in this course, we will be attempting to provide a numerical solution. But there is an analytical solution to this problem. And here we start with Newton's second law. It says that the net force acting on an object, a body, is simply the multiplication of the mass of the body and the acceleration. Or acceleration of a body if there is an acting force of F and a mass of M can be written in terms of this acting force and the mass. And we, on the other hand, we know that acceleration is related to velocity through this equation. So time derivative of velocity gives us acceleration. Then we can insert it into here and write down an equation. In our bungee jumping problem, we have two forces actually. One is the downward pull of gravity. So there is a force here, which is, let's say, F(d), downward pull of gravity. And there is another force, which is about the air resistance. That's upward force of air resistance. So Fu. So the net force is going to be sum of these two. And their directions, as you can see, in opposite So then the forces might have different magnitudes, but the sum will be the net force. Here, Ft is simply m times g from Newton's law of gravity, and upward force, the air resistance, is about the direct coefficient, and it can be written as minus CD V squared. Okay. So then we can write this equation from this Newton's second law. Okay, so we derive the differential equation that we have stated in the very beginning of the presentation using some basic principles of physics. Now, the solution to this problem, so this part is mathematical modeling. Now, this part is analytical solution to this mathematical formulation problem, which is a differential equation here. And there is a very well-known solution to this simple equation. And from mathematics, we can find this analytical solution. Okay, let's see on an example here. There are some unknowns in our equation, so we have to write down some. We have to we have to have some inputs to determine the terminal velocity. Here in this example, the mass is given as 68.1 kilogram, and there is a stationary balloon here, and this guy jumps from the stationary balloon, which means that the initial speed is 0. Okay. Now determine V of t at t equals 12 seconds. So after 12 seconds, what is the terminal velocity? By the way, the air direct coefficient, CD for air, is given as 0.5 kilogram per meter. So with this inputs, determine the speed at t equals 12 seconds, and determine the interchangeably use velocity and speed. There's a difference between them, but please forgive me. Just imagine that I'm talking about velocity. So determine the velocity when t, the time, tends to infinity. Okay, this is another part of the question. So there are two, 1 and 2. The first one, the velocity at t equals 12 seconds, and the second one, velocity at t equals, t tends to infinity. Okay, then we can simply use analytical solution and insert all these numbers and see that for any t, we can write down v of t as an hyperbolic tangent function. This is a an interesting function. It's better to plot it. For any t, the hyperbolic tangent, let's use a different color here, is just about this, which is 1 and minus 1. So it is hyperbolic tangent t. Okay, as you can see, for positive t, so this range, when t, let's say, equals 12 seconds, we need to solve this equation. Okay, here. So it seems that there's a smoothly varying function here, smoothly varying function, and tends to unity when t goes to infinity. So the answer to this is quite clear from this function. When t tends to infinity, this function goes to approximately 1, which means that this goes to this number. Okay. So let's see. So here you can see the terminal velocity, so v of t, for the time instance from 0 to 12 seconds. For 0, it's 0 stationary. And when t becomes 12 seconds, the terminal velocity exceeds 50 meters per second. And after that, it tends to be constant. If there is no ground, imagine that, very long distance, then the maximum speed will be somehow around 52 meters per second. And on the right-hand side, we can see this. This was simply behavior of hyperbolic tangent, as you might remember. Its maximum here should be around 51.7. Okay, so this one. So this was an analytical solution to the problem. Okay, next we'll look into numerical solution, how we develop a numerical solution to this problem. Here, note that the function is a smoothly varying function, right? This is an important knowledge, important information when we attempt to numerical solutions. So for numerical solutions, we usually look into the methods where we use only the arithmetical operations. So multiplication, division, multiplication, summation, subtraction, like this, so that we can implement it on a computer. Then we may go to the differentiation first, because we are dealing with the differentiation. So time derivative of velocity. And we know that time derivative of velocity, or simply delta v divided by delta t. So simply how much speed varies when there is a very small amount of time change. This is from the definition of differentiation. If we take two points, let's say ti and ti plus 1, and the time derivative of v will be the difference here divided by this difference. Okay, this is called slope of this curve. Okay, remember that this is somehow our hyperbolic tangent. Okay, with some coefficient, let's say. So somehow then we can use this in here, okay, and write down this equation. Okay, so then we can continue what we call Euler's method. Euler's method is simply is an approximation using slope. Any speed at time instant I plus 1 can be written in terms of the velocity speed at ti, so the previous value of the velocity, and the time increments. So you can see the value of the speed any time is dependent on the value of the speed in previous time instant and the difference. Okay. Considering this, I can write, okay, this is equivalent to this one. So insert it into here and then write down the velocity at I plus 1 in terms of velocity at I and the time derivative of the velocity at I. So here you can see that the new value of the velocity, so ti plus 1, is simply the old value, so vti plus the slope, which is dvti divided by dt times the step size, which is the difference time. So ti plus 1 minus ti, or delta t. Okay, so based on this methodology, iteratively we can calculate the velocity starting from, let's say, t equals 0, and then determine it at t 1 second, for example, next t 2 second, and then continue in that way. At the end, we can estimate the velocity, terminal velocity at any time instant t. Okay, let's see then the same example. This was the Euler's equation. I mean the finite difference approximation, what we call is finite so we only need the initial speed, velocity, and the slope of the velocity and the timing. So here, for example, we take the first, that was, as you might remember, stationary. The jumper is in a balloon, and balloon is stationary. So the initial speed is 0. Then the speed at any t can be calculated using this formula, which is, let's say here is t is 2 seconds. So you can imagine that that's ti plus 1, and our ti is 0. So it is 19.62 meters per second. Next, the next iteration. So it is going to be again, if we add 2, then that's going to be 4 seconds. So increase one increment, one step size, 2 seconds again. Now the initial speed is not 0. This is the initial speed. And then the terminal velocity can be calculated as 36.4137 meter per second. So we continue with this with the time instance from 0 to 12. And we calculate the velocity at t equals 12 seconds is 51.60. So on the right-hand side, you can see this was the analytical solution. Parabolic tangent, hyperbolic tangent, as you might remember, k times somehow a t, something like this. So if we look at the approximate solution here, as you might remember, numerical solution is an approximation to this one, as we have used this iterative finite difference approximation. You can see the exact solution in the approximation. There is a difference, there is an error here, and the next lesson actually will be talking about this error, how to formulate, how to quantify this error. We'll be talking about accuracy, precision, and numbers.